Um, and this yeah, for anybody who might be attending for the first time, the format of these talks is very discussion oriented. I want lots of questions because that way people actually can understand, and I'm fine with like we don't get through too many slides. If like often the discussion will cover topics that I was planning to cover anyway, and I think it's good if things come up through natural discussion. I think if I'm just delivering slides, it's easy for eyes to glaze over and people not to comprehend as well. Um, so far, there have been lots of questions very naturally and easily, but towards this end, I've been having an appointed interviewer every time whose job it is to ask the questions to make sure that at least they understand what I'm talking about. So, uh, I, yeah, I think Paul and Norman, both of you haven't served as interviewer yet, right?
Yeah, I was about to ask. If you want, I can do that this time.
Sounds good.
Or if Norman, if you'd prefer.
No, I there's a chance that I couldn't stay to the end because I have to get up very early
Right.
tomorrow. So yeah.
In that
Thank
case,
you.
me it is.
Cool. Sounds good. So,
Right. So when last time we left off, yeah, it looks like we were talking about tiling properties of UDT 1.1.
yep.
Digging back to right, and there was this whole thing about this chain from informal intuition all the way to implementation in code, where we have this like philosophy world and this CS world. Is that
Yeah.
right? That should be like a couple slides ago. Or did I?
It's here.
There we go. Yeah. Okay, a few slides ago. And then after that, major crux. How well does this hold up? Do we have insights that transfer effectively from like the very start of that chain to the end? And there's a weakness to the UDT 1.1 formalism where we where we model self-modification as always deterministic, always discrete, and always having known result in advance. Is that about right for what was going on in the last few slides? Yeah, there we go.
Yeah, and they're talking about the weakness and talking about so to me, UDT 1.0 is the more promising formalism for tiling, or we could come up with some third formalism that's maybe somewhere between the two somehow. But I'm going to talk about UDT 1.0 tiling results next. Mateusz?
So I know that Diffractor has written something about UDT 1.01, which sounds like, yeah, let's backtrack to UDT 1.0 and do something else.
Yeah.
I don't know what exactly it is, like, so you are probably familiar with it. And so, yeah, is this something in line with what you want to do?
Yeah. I've like this project was a result of interacting with me. Like I've talked to him about it. He says that his sequence on it is unfinished. I don't understand it entirely. I would be interested in getting him in as like a guest speaker in this talk series sometime though. Yeah. So this was like I worked with Martin Soto on this stuff over the course of one summer, and then Martin couldn't work on it anymore, was prioritizing other things, and I asked Diffractor if he wanted to try to pick up the research, and UDT 1.01 was basically what he came up with. So yeah, very much in this kind of line of research. Although definitely not exactly the approach that I'm going to advocate here in these talks. Yeah. So any questions before we jump into the next proof?
Maybe like
No?
refresh. Maybe refresh on this proof. I'm not sure I quite understand the proof of UDT 1.1.
Oh, refresh on this one? Yeah. So yeah, this one's very simple. Like, so you have the fairness assumption. Do you understand the fairness assumption?
Yeah, so for every policy such that like the after modification for every pair of policies such that after the modification they are like the same policy over trajectories, they like give you the same expected utility if you assume that you are like starting with this policy.
Yeah. So it's like if the effective policy is the same, the expected utility is the same. Very, I mean, you could imagine stronger conditions, but it's a very strong condition.
Could you remind me, or remind us all what it means to have those upper guillemets there, little ceiling quotes?
Yeah, so those are similar to like for Python programmers, it's like F strings, but it's like you were evaluating intuitively, like in terms of programming language users are like evaluating whatever in those quotes. So it's like the reason that I'm using those quotes at base is because I'm using the same meta language, so the language that we use to talk about the agents, and then the language that the agents use internally. So like whenever it's wrapped in an expectation or wrapped in a probability statement, it's I'm using the same notation, but there's an implicit conversion to like the agent's own internal language happening, right? So like pi star for us means the policy actually chosen by the agent. And pi star for the agent means like in the agent's language, the policy chosen, but it's not like the full written out policy. Like the fact that it's using pi star doesn't mean it knows what the policy is. It just is like, it's like the pronoun I. It's like pi star equals something is like, I do this, right? And so then when I do use the quasi quotes, the little corner things, then that means that I'm not just talking about the agent's internal language. I'm like in our meta language again. And I want it to be evaluated. And so the pi2 there in the quasi quotes should be understood as evaluating to an actual written out finite description of the policy in the agent's own internal language. So it's differentiating between two different translations from like our meta language for talking about the agent to the agent's own object language. One where like instead of just the agent knows the bare term, like if the quasi quotes weren't present, then it'd be just like, oh, okay, so pi star equals some pi2, like that's just a term that hasn't been defined further. Instead, it's like, no, I want the written out policy. I want it to know in detail which actions lead to which, which observations lead to which actions.
Okay, so just to make sure I've got this right, based on the notation slide you had a few slides ago, what the fairness assumption states is for all policies pi1 and pi2, if the agent that you are and the action that you take because you take policy pi1 is in all cases the same as the agent you become and the actions you take for policy pi2, then your expected payoff for utility, if the policy that you actually have is this pi1, should be the same as the expected utility if your actual policy is pi2. Is that correct?
Yeah.
Where what I'm saying, the agent you are and the action it makes you take, I'm specifically talking about how M of policy means actually do this policy, unroll the whole thing, make all the prescribed self-modifications, Yeah, pi star is like pointer, where like I would say having pi star. I guess I have some slight notational issues with the pi star then. Just as a matter of
Oh,
taste.
so is the star supposed to stand for a pointer like in C++?
No. All of them, like if I don't put quasi quotes, then it's like a pointer. Like it's not like because it's the star, like the well, I suppose you could think of it that way, but that wasn't my intention. I'm like the pi star is just a bare symbol that like the agent knows is some policy, like it is understood to have type policy, and it's understood as the policy that the agent does. And what I mean by it's understood as the policy the agent does is if like we have additional information encoded in the prior about like consequences of choosing certain prior policies, then it would be formulated in terms of this particular symbol.
Okay, so let me make sure that I've understood this correctly then. When we write pi star here, what we mean is the actual whatever policy our agent is currently considering. Maybe it's the one it has, maybe it's the one it isn't, but this is supposed to just be, this is a whole ass policy here. And whenever we put something in quasi quotes, what that means is this is what it would actually mean to go unroll and do this policy. We're not treating it as a variable or as some abstract plan. Here's the actual whole decision tree. No?
So
There's
with respect to the first part of what you said the policy the agent is considering. I'm like, no, it's not just the policy the agent's considering. It is more like a pointer to whatever the final one that's chosen is. Because remember, in the definition of UDT here, I'm like,
right. You have your pi star there as well.
like what we're conditioning on. Oh, this should have quasi quotes around it, actually.
Okay,
So,
that was a little confusing.
yeah, I should make a note of that.
So equals here is not equal so much as is given by, or here is the whole description of it. When we say pi star equals presumably quasi quotes pi.
Right. This should be quasi quotes. Yeah.
So then that equals is not so much an equals as is given by, or here is the form of this thing.
I'm not sure what you mean by that. So
otherwise it's just type errors, right? Here's this one thing with type policy, and here's this other thing which is contained, which can naturally be identified with something with type policy, but doesn't actually have type policy itself.
if I say A equals 2, where A is a variable and 2 is a real number,
Yes.
have I committed a type error?
Only if you want me to believe that that equals means it's identical to. If you want to make that a colon equals, sure, not at all.
It seems to me that if the equal means identical to, I can still have variables in my language, right? Like having equals doesn't prevent me from using variables that are of a type, right? This is just like,
I'm just saying that I want to make sure that we carefully think about what an equal sign means.
So I think Paul is like trying to make a distinction between equals as a definition, as you said, colon equals, and equals as a statement that the two things are the same. But Abram is using this in the context of variable assignment.
Like this makes sense. This distinction makes sense in the context of programming, but in the context of logic, we like.
Well, the issue for me, at least, is that there's a little bit of notational unclarity. On the one hand, this could be saying, the expected value, the expected payoff, given that it just so happens that these two things are identical, or it could be the expected payoff, given that the policy is this specific description.
Are you making like a causal, like we intervene to make the optimal policy into the one that's given? Because
maybe it's just a matter of framing.
Right. Like I'm like, I think this distinction that you're bringing forward is meaningful in the context of programming, but not meaningful in the context of logic. In logic, if we say that a free variable equals some term of that same type, but it's not a free variable, then we are saying, well, it just so happens to be. There's not a distinction between just so happens to be versus equals by definition in logic. It implies all the same things.
Okay, I just want to.
At least, standard logic.
Yes,
Of
mostly
course,
I am having a little bit
we'll
of.
try to make this distinction.
I mostly just want to make sure that I'm understanding things here correctly, because a lot of this is fairly new and the notation is a little bit to wrap my head around.
Yeah.
But I think I've understood.
Okay. Yeah, I think the only mistake here I've made in terms of how I want to frame it is I've omitted these quasi-quotes around the final A in the top one and the final pi in the bottom one.
So why does the action also need quasi-quotes?
Because the action is taken in our meta language, like the argmax outside of the expectation, that's like our language talking about taking actions. And then when it goes in, it's like we need to like evaluate it to the specific term for that action in the agent's language, as opposed to like just the A that I've written. So it's like the argmax A here is like binding the variable A to some action from that set. And then the quasi-quotes are like evaluating, okay, what A was it bound to?
Okay, I see. Okay, was it? Yeah, okay, I think I see. I've also realized I've been terribly derelict at reading questions from the chat. So first off from Linda, are there implied do operators here? I don't think so, but I'll let.
Yeah, there's not implied do operators here. WayDie wouldn't want that, but it is an option. Like for those who are more CDT minded, that's causal decision theory minded, it would make sense to do that.
And the second one, which variable is free in the expected value expression, pi star or pi or both? I don't know that either one is. Possibly the pi star.
Oh yeah, I think I see why there's a confusion about that. I was using the term free variable when I was saying, well, if you have a free variable A and you set it equal to 2.
Yes.
I think I should have said constant, right? Like,
yeah,
if you have a constant A and you say, well, it equals 2, then yeah. So it's, yeah, pi star is a constant, not a free variable. The pi is a bound variable, bound by the occurrence of pi in the argmax, and there's no free variable.
Okay, that makes sense. So yeah, so here our pi star is getting pi assigned to it, and pi itself is defined by being the argmax over these expected values.
Sorry, I was really distracted by.
Oh, I was going to say the
chat.
It doesn't seem like either of these are, yeah, so neither of these are free then, because pi star is getting this pi assigned to it, and pi itself is defined by argmaxing over this expected value. So neither of them is free.
Oh yeah, so right, yeah, I agree with that. Vladimir Nesov said in the UDT 1.1 line, there's also a pi star on the left side of the equation. So, yeah, that's us in the meta language saying we know that the policy actually chosen by the agent is defined by this expression on the other side of the equals sign. Right? Like we know that this is the policy that's chosen because of like the agent source code.
Okay, yeah, pi is free inside just the expected value thing. Actually, I'm still not clear on that, right? Because that pi should be in quasi quotes, should be like, actually, this isn't the real policy pi that would maximize this thing. It's the description of this policy pi. It's the things you would need to do if you wanted to have the policy pi.
Can you see my mouse when I move it around or no?
Yes.
Okay, so you mean this pi?
Yes.
Okay, then yeah, that made sense to me.
Can I ask a question about like I'm not sure whether the fairness assumption is compatible with the current way of defining like the M function, the unrolling of self-modifying
Interesting.
policies. Yes. So let's imagine like what one of the like the self-modifying policy has like like there are two possible observations, and one of them will trigger self-modifying, modifying the action for the other observation. Is that clear?
Sorry, can you just repeat?
Okay, like two observations. This policy is defined for two distinct observations, and for the first observation, like there's no self-modification. But for the second observation, there's a modification of the action you would take in the first observation.
Okay.
So now, like, so the unrolling of this, this policy after it is unrolled would already give the first observation the action that's that is dictated by the self-modification, right?
Yeah.
So, but now imagine that you encounter the first observation first, like temporally first.
Right.
Then you would take the action before you modify.
Right. So we shouldn't have been like in the decision problem setup was wrong. Right? Like we shouldn't have been allowed to select the self-modifying action for the second option if it wasn't 100% effective. So if there was a chance that we might encounter the first observation first, such that the second action hasn't had a chance to causally influence it, then it's invalid for the second observation to have a self-modifying action concerning the first observation as an option available to it.
So you're saying that this is what the fairness assumption amounts to, like or is it like extra?
Yeah, this is an extra assumption that is at the bottom of this slide. That there is
this is.
Sorry, yeah, I guess it's not.
I thought this was just for the unrolling of the policy.
You're right.
Like
you're
in the it's not related to.
Yeah, is an extra assumption that I haven't written down. My apologies. Is that an extra assumption that we only this should say like there's a well-defined limit of running the self mod, i.e. the effective policy and this is like realistic or something. Like, I guess, yeah. I didn't write it down because I'm not.
I think you kind of implicitly implied it when you say that there's no outward behavioral difference between the self-modifying policy and the unrolled non-self-modifying
I
policy.
think it's kind of implicitly like in the definition of the set of modifications, right? Like each self-modifying action is associated with a set of modifications. We could all say like which will occur with certainty, like which will be effective. Like if that option is available for the second observation, then it must be causally effective, which means that if we don't have any time travel shenanigans, then observation 1 has to happen later than observation 2.
So it's like you have like the real world, the decision problem should have the same causal structure as the way you unroll your self-modifying policy.
Yeah, right.
But that's like, isn't that like knowing the future? But like, why could we?
It's knowing the decision problem, right? Like it's like I have specified a decision problem. It is a strong assumption. Like I will agree with that. It is restrictive. It does not allow me to deal with cases where self-modification might be an uncertain business. It only allows me to deal with cases where if I have an option to try and self-modify, then it will work 100%.
So basically, like colloquially, it's like the self-modifications dictated by the policy are tailor-made for this decision problem.
Yeah, yeah.
Okay.
Which is like somewhat unfortunate, but that's the easiest formulation that I could give.
Okay.
So a couple quick things. First off, Vladimir asked if there's a fixed point outside the whole equation, which is the thing that binds pi star within the equation and defines it in the end. And I wouldn't call that a fixed point. It's a search over all of the policies pi that you could have as your description for what the agent's actual final policy pi star is. And that is, in fact, what binds pi star, but I wouldn't call it a fixed point. It's just, this is whatever thing I could plug in here and roll out into a description and assign to my policy.
There is a sense in which I need a fixed point. So it's not a fixed point in the sense of like pi star here, as in like the actual tabular policy that pi star represents, does not depend on the actual tabular policy. Like this isn't a fixed point on what policy is chosen for pi star. So it's not a fixed point in the space of values that pi star takes. But if we wanted to define this UDT 1.1 or the UDT 1.0 there properly, like as a program, it would be a quine because we're like, we have to like you're writing out like, actually, do you need to do a quine? So like if I wanted to do something like, instead of writing pi star, I wrote like the source code itself, right? So it's like the system knows its own source code, and it's like considering, well, what if the output of my source code was pi? Then that sounds impossible because you have the whole source code, and then in one part of it you have like the source code again, so it sounds like it would just be infinitely much source code. But we can do something that amounts to that with a quine. Do people know what quines are? What I'm talking about?
No.
Okay.
I
Okay.
do, and if you
So
want, I can explain it.
yeah, that's
I would say that the simplest example of a quine is you could totally write down some Python code that when you run it, prints out the Python code itself. That would be a classic example of a quine.
yeah. And so we could put an in that pi star instead of writing just pi star there, which when evaluated amounts to the whole argmax itself. Using the trick of quining. But that's not what we're doing here. So that quining is a sort of fixed point that is kind of involved here. But here I'm just, instead of doing that, I'm just saying, well, we have this constant pi star that lets us like refer to the whole decision made by the agent. And so I think I'm avoiding any need for fixed points actually.
As a
You
much more
said a
minor
couple of
note,
things.
how much? Sorry, what's up?
Yeah, go ahead.
I was going to say, as a much more minor note, how much do you care about catching like random spelling errors in these slides? Because I've already found 2.
Oh yeah, I mean that would be nice.
Well, there was the word available in the notation slide, I think.
Okay.
And there was a regarded with the GU in, I think it was a slide about M of whatever. Like this is regarded as something or other, and it was a GU in there. As in like regarded.
Okay, I guess I'll look for that one on my own time. But I've corrected the other one.
Here, yeah.
So,
Chosen policy pi star is the input output function associated with the agent source code regarded mathematically. That slide.
okay.
But yeah, just things I picked up.
Yeah.
Hopefully, we will cover anything new today.
Right. But we were in the middle of refreshing on this period. So yeah,
Sure.
fairness assumption covered. And then we're just saying, suppose for contradiction that there is some self-modifying policy that we strictly prefer to all non-self-modifying policies. And then we're just pointing out that the effective policy of that policy is non-self-modifying and should have equal expected utility by fairness. Therefore, contradiction with initial assumption.
So
So
let me make sure that I've understood what's going on with this proof properly.
Yeah.
By fairness assumption, if 2 policies would make the agent be doing the same thing, then they should give the same payoff.
Yeah.
Step 1. Suppose we had for contradiction some self-modifying policy pi and some non-self-modifying policy pi prime. So for any pi prime, like fix our pi that is self-modifying, and assume that for any pi prime outside of a sub m, our expected payoff, if our policy is pi, is strictly better than our expected payoff if it's pi prime.
Yeah.
However, by fairness, 2, should always be the case. Yeah, it should always be the case that if our agent's policy pi star is given by this pi, which is self-modifying, then that payoff should be the exact same payoff as if the agent's policy pi star were given by this version m of pi, where we've already unrolled. Hold on. I think I misunderstood this part.
I think the step 2 is saying that, well, m of pi is a non-self-modifying policy. So, and so like m is idempotent. So if you do
Removing them.
m of pi, can you hear me?
Yeah, I can. Yeah.
Yeah. So if you do
M of m of pi should just be m of pi. Yeah.
Yeah. So m of pi is equal to m of pi. So by first assumption, they give you the same expected utility.
Now that part I understand. The part that I think I'm hung up on now is, why do we know that m of pi is non-self-modifying?
Because it already executed all modifications.
Yeah, so that's based on this definition. So like,
Okay, so it is in fact
like running an individual self-modification means like removing it and making all of its changes, and then there is a well-defined limit of running. So I'm not just talking about like finitely many steps, but if there's like, even if there's like an infinite chain, there is a limit of running all of these, which means like that limit there can be no modifications that we can continue to make by running, right? So we've removed all of the modifications. This could be more clearly spelled out, but that's the idea here.
Yeah, arbitrary webs of
Oh, do you still want this?
self-modification can create race conditions or loops, right? Okay, I think I'm confused then, because I would have thought that having your policy be m of pi involves first modify yourself such that you now do the self-modifications that pi would have you do. Is that not correct, or no?
This running part, like you replace each, so like for a self-modifying action, you replace it with its non-self-modifying variant.
I see.
And then you replace the actions that it tells you to replace with what it says to replace them with, both at the same time, right? So we are removing a self-modifying action. We might be adding more in, but then we're going to remove those next when we're trying to get to this limit. I do see a hole in my definition where, like, imagine that we have one self-modifying action that says only to enforce itself. It's like,
Yes.
whatever other action is, I put in myself here. Then if we kind of remove it, replace it with its non-self-modifying variant, but then put it back. And like this definition here doesn't really say. So yeah, I want there to be the implication that the effective policy has no self-modifying actions. I think I have failed to achieve it due to that loophole.
Yeah. But apart from that, okay, so then I guess I did understand it better than I thought I did, because I was modeling m of pi here as just have a mask that does the things that the modified version of you would be doing in the situation, except without the part where you actually self-modified.
Yeah.
Okay, so then step 2 in that proof is saying having that mask that should be having that mask that would be taking the actions that you would be taking if you had self-modified according to pi, that is in fact indistinguishable. That gets you the same payoff as actually self-modifying.
Yeah.
But this is a contradiction because we just assumed that this non-self-modifying policy is strictly dominated.
Yeah.
It isn't.
Sorry, shouldn't your last sentence be like, we just assume that the self-modifying policy is strictly dominated?
No.
You
So
said no.
step one is saying that the self-modifying policy strictly dominates all non-self-modifying policies.
Oh, sorry. My English is like, is a language mistake. I heard wrongly.
Not a problem. Yeah, I was a little bit unclear.
Okay. We good to move on?
Thankfully, yes, with a whole 15 minutes to go.
So, yeah, based on some discussion in the private channel, I'm thinking we're going to go somewhat over what we are the usual in time. But yeah. So here's my analogous proof for UDT 1.0. So our modified coordination assumption for, or sorry, yeah, we now need a coordination assumption to kind of fill in the gap between UDT 1.1 and UDT 1.0. We need, like, the coordination failures that UDT 1.0 can have can create real tiling failures because it creates a real reason why you would want to self-modify. So we need to assume this coordination assumption, which says that if some other policy is considered better than pi star, ooh, that's another place I think I need brackets. So yeah, if some other policy, which should be in brackets, is considered better than pi star, then the
May I try?
yeah.
Let's say we've got, it should always be the case for any policy pi and any observation our agent could see O, that its expected payoff, that if its expected payoff for having pi is at least as good as its expected payoff for having some other policy pi star,
Wait, yeah, this is completely wrong.
then that should still hold up for every
Yeah,
single
yeah.
observation you could see, which, yeah, I agree, that seems wrong.
This-
That's just
this-
wrong on the face of it. Having
like,
expected value to be better doesn't mean that you're always better for every observation you see.
no, that's my intention here, but I've written it in a really weird way. So
But that still doesn't seem correct.
it is a strong assumption. Or maybe I'm misunderstanding you. Can you repeat?
Yeah, I'm saying that for every observation you see, it should not be the case that. So I'm thinking, for instance, about have a dice roll, one, D6 dice roll, and you get paid. And you get paid if you get the number, you get paid equal to the number you guessed if that number is what came up. And you can absolutely come up with different policies such that one of them is better than another, but doesn't beat it no matter what number comes up on the die. It's better in expectation over all 6 values, but one of them will say always be correct when it guesses it 2, and the other one will only be correct half the time. Or will only ever guess 2 somehow when it shouldn't. It shouldn't always point-wise win.
Right. So,
but this coordination assumption implies that it does in fact just always point-wise win.
yeah, the idea is like, suppose that I have a policy that I think is overall better.
Yes.
than another policy.
Mhm.
And now I'm given the opportunity to change a single action in my policy to the single action taken at that observation in the other policy. So like changing a single policy point, I should say.
Yes. Yep.
I should not prefer that. That's the idea. And so this is like, yes, very strong. It is not always the case for like every,
Oh no.
but it's like,
Oh, this is sorry. I think I had notation issues here. You might want to change the notation you're using.
yeah, I wish I could live.
I star
do
is
it.
its current policy, right?
Right.
Okay, that's what's confused me then, because I'm not sure. I thought this was saying that let's say we have two policies that the agent could already have pi and pi star. Or let's say we have some policy pi, which
Like
is
we get
always
like
existing.
pi 1 and pi 2, say.
Okay.
Which
then
I think
neither
is the
of these.
version in the paper is pi 1 and pi 2, not pi and pi star.
Okay.
That's not true.
Not true?
I just
Okay,
checked. Yeah.
thanks.
This still seems like I get what this coordination assumption is saying. It says that it should always be the case where if one policy results in better payouts on expectation than another, then it should also be the case that borrowing one action from that better policy should give you a better outcome than not doing that. But I'm not convinced by that.
Well, consider the like the example that I keep giving for
For
coordinating.
every observation, I would agree with this completely if it said exists an observation. For all policies pi for which this holds, there exists an observation for which this is better. But I'm not convinced by it with the universal.
Interesting.
If you want, I can try and explicitly construct an example too.
I mean, this makes sense if you like overall. If this is supposed to be like an expectation over all observations, if you pick any observation at random and replace.
Right, but that's not what it's saying. It's saying for all observations, do the thing. For all observations, this holds. And that seems too strong.
Yeah, then you would have to have like an expectation of observations outside of that.
Sorry, Abram.
Yeah.
Please correct me if I'm mistaken. But isn't your philosophy for this like current version more like let's just see like what assumptions we seem to have to make in order to make the theorems?
Yeah, this is like sort of exactly the assumption I need for this proof idea.
Sure, but
it is very strong, but you're saying it's inconsistent.
I'm saying it's unsupported. I'm saying that you can absolutely have some variety of policy which is better in expectation, but not strictly better for every observation you could possibly see.
But this is
you win 2 more points here and you lose 1 here.
So you're saying there's a weaker assumption that we could make.
I'm saying that there's a weaker assumption we would need to make because the assumption you've made here is unsupported.
I think
what's unsupported mean? It's an assumption.
Yeah, what I mean by unsupported is I can absolutely think of here are two policies.
I think we
were
mistaken. Abram is proposing the coordination assumption as an axiom.
Right.
Okay. I mean, I'm still unclear as to where it is that leaves here. We have two policies. We have 4.
Yeah, but the assumption is that such policies don't exist.
Right. So are you saying it's inconsistent, or are you saying it's just a very strong assumption that you don't like it because it's very strong?
Neither. I'm saying that this seems to imply that all policies are linearly orderable.
Yeah. But I mean, it is a very strong assumption. I'm not quite sure what you mean by linearly orderable. Like,
I mean, again, what I'm trying to say is, let's say we have two policies, and if I pick policy A, which has the better expected value, I'm advantaged by 5 points on outcome 1 and 2 points on outcome 2, but I lose a point on outcomes 3 and 4, as opposed to policy B, which is the worst one in expectation. But if observations 3 or 4 were to happen, I could borrow whatever it is B should be doing on outcomes 3 and 4, and I'd pick up a whole extra point.
So then there should be this other policy that has a higher expected utility from that substitution, right? Because we've taken the best of both worlds. And so then that should be our pi star. And now since that's our pi star, since that's our chosen good policy, now we cannot any longer find such an improvement by looking at other policies that have better outcomes in specific cases, right?
Still,
So it's like, you're saying like there's observation 1, there's observation 2. Pi 1 is a policy which, like, let's say observation 1 is, it turns out that I like chocolate better than strawberry for ice cream flavor.
Yep.
And then pi 2 is the reverse.
Yes.
And policy 1 is like strawberry, strawberry. Policy 2 is like chocolate, chocolate.
Yes.
And then,
but it turns out that you enjoy that in the worlds where you enjoy strawberry, you enjoy it by way more over chocolate than the worlds where you marginally prefer chocolate over strawberry.
okay.
So
but we get to observe whichever one we enjoy. And so the optimal policy, which should be pi star, is to have strawberry when we observe that we like strawberry and have chocolate when we observe that we like chocolate. And so what this assumption is trying to do is say that pi star is indeed that one, that we can't find some other policy that we prefer to substitute one of the actions.
Okay, so the pi star here is not some generic policy, it's the one that comes out of the argmaxing.
Yeah.
Okay, it would have been helpful if that were more clear.
Okay.
Because right now I just thought, oh, okay, so we have arbitrary policy pi and some other policy pi star, which is defined here by being at most as good as pi. And not, this is the special one that we got from the argmax definition.
Yeah, okay. Yeah, pi star is
Yeah,
always going to the specific one, pi star the chosen policy.
Okay. Okay, I'm less worried about this now then. So now this is saying for all generic policies pi and all possible observations O, if it were the case that the expected payoff, if your policy were pi, were to be better than your expected payoff with going with whatever you're doing right now, then it should still be the case that the modified policy, where on seeing some action O, you just do the pi thing instead, like this generic special pi thing that we've chosen, which happens to somehow be better than our current policy. If we were to borrow one of its suggestions for O, then our outcome would be better than if we don't do that.
Yeah.
Okay,
So,
that makes more sense.
So consider the example of discoordination that I gave. UDT 1.0 can end up in a situation where there's like if it's you put it in a red room, and then you erase its memory, and then you put it in a green room. In both rooms, you ask it, do you want $5 or do you want $10? And you give it whatever it asks for, but only on the condition that it agrees with itself in both rooms.
Right.
And so this is saying, like, in the bad equilibrium where UDT asks for the $5 because it suspects that its other partner will. So it's the red version of it is like, oh, I think my green self might say $5, so I have to say $5 or I'll get nothing, and vice versa. This is saying, well, then pi, we could find the pi, which is asked for $10 both times, that has a higher expected utility than the pi star, the actually chosen one. Now that implies that on individual observations, it has a higher expected utility. So it implies that I need to think, oh, it's better to ask for the $10 individually. Therefore, that scenario is ruled out. Like, we've contradicted this coordination assumption by virtue of not meeting that condition that, like, we have to be able to, like, there is a pi that meets the condition that's higher than our pi star.
Mhm.
But it contradicts the second half of the coordination assumption that we need to be able to take individual actions from that pi and just do them, and it should just be better. Therefore, that's not allowed. Therefore, to meet this coordination assumption in that decision problem, UDT must choose the 10.
Yes.
So the coordination assumption is working as intended in that example.
Okay.
That's how it's supposed to operate.
I think I understand this better now that it's more clear that pi star here is like a special distinguished symbol of this is the policy that the agent has.
Okay, cool.
Which I don't know if other people have had the same problem, but if they have, you might want to change the notation to make it more clear that, like, this is the agent, this is the thing that the agent actually currently has.
What's your recommended notation? Because I don't know. To me, this was the most standardish thing I could think of.
Well, without, I mean, we don't really have a notation for the agent that has these things, so probably not that.
I think I was confused by something you said about pi 1 and pi 2, like, I don't know, 10 minutes earlier.
Yeah.
Because I thought you said that you want to use pi 1 instead of pi and pi 2 instead of pi star.
Yeah,
that was my mistake. Norman corrected me. I was
all right. Yeah, but I think what's on the slide that makes sense for me.
Yeah, I think this idea of pi star, like using this notation for the optimal choice, is from economics or game theory or something. I'm not sure quite where I got it from, but I think I've seen this kind of notation before.
Wait, like I think there are two senses of the policy which the agent choose. One is like just like the agent, like the previous in previous slides, like the agent is choosing this policy. So you're saying like pi star, but you could. But here, from Paul, your discussion with Paul, it seems like this pi star is meant to, like, say specifically like the UDT agent, the agent that argmaxing this way. is choosing that policy.
Mhm.
So I think maybe like a way to write it is like that, let's say pi1, that pi1 be the policy that the UDT agent chooses. And so and replace all the replace the, you know, like the pi star in the on the left hand side of the implication, and the pi star in the quasi quotes by pi1.
Those are two different things, yeah. Or if they're not different, I think they happen to be different. I think they happen to be the same thing here.
I think this first half of the equation is bad. I'm conditioning on something that doesn't have Boolean type. I have not written the correct thing here.
Yeah.
This should be like both of the, like this one should be pi star equals and then pi in quasi quotes, and this one should be pi star equals pi star in quasi quotes.
No, but pi star is just like this notation you use for agent choosing this policy, but like, well, our theory is supposed to convey that the agent is is choosing this policy in a specific way. So I think the notations, if I were to do it like this, the notation of these two would be
totally different letters, probably. The more I think about it.
So I think I kind of understand what you're saying, but I'm like, these overlap, right? Like if I can have a notation for just like the agent chooses the policy, whatever the agent is like. And I can have a notation for this algorithm chooses this policy, like UDT 1.0 chooses this policy, UDT 1.1 chooses this policy. Which is then the same as like saying this policy is the optimal policy in, or amongst the optimal policies in the UDT 1.1 sense or the UDT 1.0 sense. Those are going to be equivalent. But if I just use this, like if I just use pi star as like the agent chooses this policy, then the additional question is, well, does the agent know its own source code, right? Like this, so like pi star is going to be equivalent to whatever this other notation is if the agent knows that it has this particular source code that makes it just choose the optimal thing in this case. Otherwise, for the agent, it's not going to be equivalent because the agent doesn't know its own source code. Although for us, it might still be equivalent because we know the source code. I guess all I'm trying to say is like, it's not clear to me that I need to notate it differently. I can instead just use pi star for the thing chosen by the agent and then provide additional context for whether we know that the agent is choosing in a UDT 1.1 optimal way or a UDT 1.0 optimal way, and whether the agent itself knows that.
So in this way, the coordination assumption, you would like it to be independent of the theory. Like this is an assumption we could make for any theory that chooses an optimal policy, and it constrains the optimal policy to, it constrains the other policies, the relation of other policies to the optimal policy in a certain way.
like, I can take this coordination assumption and I can think of a different agent and say, like, is this coordination assumption inconsistent with this agent, or like ask these kinds of questions. Sure. I don't feel.
I think I'm gonna. I was gonna
Sorry.
say I think I'm gonna side with Norman here, unfortunately, and say that it is still a little unclear when we don't know whether pi star is referring to the policy that the agent has right now, or the policy that the agent picked through this argmax process, or the policy that the agent got because it started with this argmax process and then self-modified, or is wearing a mask, or
Pi star is the policy chosen through the argmax process. It's not the effective policy unless it happens to be equal to the effective policy. It's the policy that pops out of the argmax.
No,
Or-
okay. I think Paul pointed out the key thing. Like, so if that's the case, if you are using pi star, like you are
Going on line
reserving
two,
pi
then.
star exclusively for optimality, then why use it like for all these
What's-
expectations? Where
Yeah.
you say like pi star is equal to blah blah. That doesn't seem to be consistent.
Gotcha. So it's like, if I understood you correctly, you're saying like, in the meta language, I'm using it for the thing that pops out of the decision procedure.
Yes.
The chosen policy, not the effective policy or anything else, the chosen policy. Then when I'm using it in the internal language of the agent, where I'm saying like pi star equals yada yada, I'm using it as the I of the agent. And these are two different meanings, in particular in the case where the agent does not think of itself as just being its source code. So effectively, my notation suggests that the agent knows its own source code, which I haven't explicitly stated as an assumption, and therefore is kind of misleading notation.
I think I understood the source code perspective now, but I really like isn't like the fundamental. There's a fundamental requirement for this expectation condition on something to be able to express like literally like anything. Like the agent taking a certain policy, which could be anything, and computing its expectation.
Yeah. Sorry, what's the question? Or what's the contradiction?
So this shouldn't be tied up with optimality, because this notation, this formalism of taking expectation condition on the agent's policy being such and such should be able to express like the agent taking any policy condition on any policy.
I think I see what you mean. I think Wei Dai disagrees. Like, I think Wei Dai's intention is for it to be tied up with optimality. The agent is asking the question when it says, like, when I condition on these things, when I condition on pi star equals pi there, or the action version, then according to Wei Dai, I am conditioning on the abstract mathematical idea that this decision procedure itself outputs this thing. So it is conditioning on what if the optimal output were this, not just what if I do this. But I agree with you that we need not think of it that way. We could instead do a different thing. And I've been ambiguous about it.
Why is it like? What's the deep? Is there like some deeper? Because I think this is, I find this very interesting. Like,
so yeah, Wei Dai is trying to say, well, you control copies of yourself throughout mathematics that are put in the same exact situation when you're deciding what you do in that situation. So if some other agent is optimizing the same, like is doing the same argmax, then you're thinking of yourself as controlling that output of that argmax as well when you compute it here. And so it's not just what if I do this, it's like what if the math does this, the math that I am does this.
oh, also, I think I get the point that this is supposed to contribute to coordination, because like the other agents, if like it's doing the same computation, if it's also outputting this optimal policy, then like the optimality coming from computation, so you could be sure that the counterfactual agent or the agent in other time points is also outputting this something like that. Sorry,
Yeah.
not yeah.
Yeah, but yeah, I see that I haven't been clear about that here, for sure. So yeah, consider it as another option, much like we could add in a do operator if we want to think about causality here. We could think of the I as being distinct from the mathematical statement, or we could tie it together as Wei Dai intended. So, are we ready to carry on with the proof?
I think so. If you'd like, I can try and read through this and see if I understand what it says.
Sure, sounds good.
Okay, so just for an assumption, let's say that for all pi that satisfy that thing, right? For all pi where our expected payoff for following that pi is at least as good as the expected payoff if our policy is the one that we get from this argmax process. For any policy that's like that, and any observation at all, then it should still be the case that if we that our payoff from following our otherwise default policy, our payoff for following our original policy by default, except if we see O, in which case we do pi's suggested action, that should still be at least as good as what we get from our argmaxing process and just leaving it alone. Under that assumption, suppose for a contradiction that there exists, I assume that there exists, we're saying here, there exists some pair of actions AM and A, such that AM is a self-modifying action and A is a non-self-modifying action. Yeah. And for a contradiction, we're going to assume that the expected payoff for the self-modifying action, if we see O sub M, is better than the expected payoff if we take A instead.
Yep.
By fairness, we know that what would happen if by fairness, we know that the expected payoffs we get for having our policy be literally just the policy we have on starting, and our policy being don't self-modify ever, but still do the things that pi star would have you do. We know that by fairness, those two things have to be the same.
Yeah.
Then by coordination, we know that this should still hold up if, hold on, should still between doing that and just doing What? So the expected payoff.
I think step 3 falls from step 2 because the coordination assumption assumes a weak inequality, of which equality is a case.
Yeah.
So this does at least as good as that. So this where it's as good as that as thing that pi star of OM would have. Yeah. So then, right. So then by coordination, so we know that doing the thing where you just pretend to go through pi star self-modifications and take all the same actions anyway, that's still at least as good as actually literally doing pi star by fairness.
Yeah.
And so we can borrow one of the things that pretending to be pi star would have you do, which is M of pi star evaluated on OM. That should still, the policy you get where you mostly do pi star equals quasi quotes M of pi star, but if you see, wait, other way, right, sorry. We're thinking about the default policy again being pi star. So the case where we usually do pi star, but in the case of seeing OM, we take the action M of pi star of OM. That should be at least as good still as the case where we do the left-hand side of 1.
And it's implicit here that if you do the left thing, if you do M of pi star on OM, then you get A. I guess that's how you are supposed to get the contradiction.
Yeah, I guess I'm not sure why it is we end up with
Yeah, me neither.
pi star of OM being AM being your default case.
Oh yeah, right. Okay. So
So what I would have expected to see there would just be pi star of.
so I think on line 1, it should be like there exists an AM such that for all A that are not in AM, rather than just like there exists some particular A. That's
Yeah,
not
there is some self-modifying action that beats out all the non-self-modifying actions.
Yeah. And then on line 3, we're saying, well, here's one option that should be not be beaten out, namely whatever the effective policy does.
Yes. And I see how that leads to a contradiction. I just, where pi star borrows its action on OM from what M of pi star does on it. And that should be at least as good as just having it run the self-modifying action.
Yeah. Does it make sense?
We know that this is at least as good as that. So pi star being that except for OM should be at least as good as just plain do pi star. I'm still having trouble with the right side of that because I would have expected that to just say pi star of OM equals quasi quotes pi star of OM. Do we know that quasi quotes pi star of OM is AM?
I'm taking the thing from the effective policy, right? I'm basically querying for, hey, what action does the effective policy do here?
I think Paul is asking about the right side.
Oh, sorry.
Yes. Like I said, I would have expected that to just be quasi quotes of pi star of OM. But maybe it's just too. Maybe I'm just literally going with the.
I mean, yeah,
how I'm carrying across
I think
the consequent there.
I think that's how AM is defined, right? Like
Is it
Maybe
though?
maybe it should be written out like in maybe like line 1, step 1, that AM is equal to what you just said.
The quasi-quotes of pi star of OM?
Yeah.
Is it though? Oh, bye, Matish. Let me look back at the. I thought that A sub M is just some generic, just some generic self-modifying action. I don't
Right.
know if
So,
it's finding anything here, but
yeah, I think maybe I agree with Norman that I should edit it in that way. I'm so like 2 is supposed to match the left-hand side of the
yes,
coordination assumption.
absolutely.
And then 3 is supposed to follow from just going to the
Right-hand side,
right-hand side.
consequent.
So yeah,
And so I'm looking at
It-
this and going, okay, if I'm carrying this across directly, then that right-hand side for part 3 should be expected value of utility given specifically pi star of OM equals quasi-quotes pi star of OM.
yeah. So I think I like Norman's modification. I think that's right.
Where AM is specifically given by quasi-quotes pi star of OM.
Yeah, but like that's what we suppose for sake of contradiction.
So it's more like for there is OM, not there is AM. There,
Yeah,
I mean in the first line, like there is this observation such that the self-modifying action as computed by the policy for this observation strictly dominates like every other action.
yeah, yeah. I think that works. Well, thanks for finding these problems. I appreciate it.
Of course. I mean, we're going through all of this with a fine-tooth comb. That's half the point of this, right?
Yeah,
Unfortunately, that also means it looks like we're not going to get to anything new today.
this was new.
This one's new. I thought we went over. I guess we went over it just briefly at the start.
We just went through this last time.
Mhm.
So this one was new, and we did in fact get through it. So we got through one new slide.
Great. What's on the next slide? Anything like substantive or
little
yeah.
bit of discussion of that. Yeah. So like this is this seems better, but if to me it feels still very dissatisfying because the coordination assumption plays too large of a role.
Mhm.
Like what I want out of a tiling theorem is that the agent is like considering its decision process, and by virtue of like something that it understands about its decision process, it can trust itself, right? And here it's just a bold assumption of coordination, which is like
Yeah.
so strong that it rules out any suboptimal action, and then it's just trusting itself because of this coordination assumption, which, as you said, is unsupported. And so the next proof tries to weaken that coordination assumption and get this self-trust in a more satisfying way. And I guess we will go over that next time, since it's been an hour and a half.
Yep. All right. In that case, I will still see most of you next week, and Abram, I'll see you tomorrow.
Cool. Yeah.
Thank you all.
Thanks,
Talk to you
everyone.
later.